Okay, this is second lecture in complex analysis, analytic functions. So in this lecture, the contents are analytic function. We will define what is analytic function, what is Cauchy-Riemann equations, uh, Cauchy-Riemann equations necessary condition, and sufficient condition for function to be analytic. That means how to find out the derivative of a function from this analytic function, and what is the sufficient condition for a function to be analytic. Then we will do some problems. Okay, so first I define what is analytic function. So analytic function. So a function f of z is equal to u of xy plus iv of xy is said to be is said to be analytic at a point z naught. At a point z naught, if it is differentiable at every point in some neighborhood of z naught. Okay, so what is analytic function? Analytic function is a function that we said is said to be analytic at a point z naught if it is differentiable. So analytic functions are differentiable function, and there is a condition in some neighborhood of z naught every point f of z is differentiable. That is what is neighborhood. That means if you take any a point z naught is here. If you have a circle or disk with radius rho, that means set of all z such that mod z minus z naught less than rho. That means if you have a point z naught, then the function is said to be analytic if there exists a point or exists a neighborhood where f of z is analytic at every point inside that circle. If such a circle exists, then we say that f of z is analytic. This is the formal definition of analytic function. So that means f of z is analytic if there exists a circle where with any radius rho where uh, f of z is differentiable at every point inside that circle. Then we say that f of z is analytic at a point z naught. Now, if f of z is analytic, then there is an important equation that is called Cauchy-Riemann equation. So next topic is Cauchy-Riemann equation, or we call it as CR equation. So what is CR equation? Now, let f of z is equal to u of xy plus iv of xy. Now, now we will call u of xy is u and v of xy is v. We will denote it. Okay. Hereafter, we will denote u of xy by u and v of xy by v. Be differentiable differentiable at z, then f of z satisfies CR equation. That is, I'm calling this u and this v. So CR equation is ux equal to vy. That means u with respect to x, partial derivative with respect to x, is equal to v with the partial derivative with respect to y, and uy equal to minus vx. That means any function is differentiable at a point z or analytic. Both are same. At a point z, the f of z satisfies Cauchy-Riemann equation. That means if it is analytic, then it satisfies Cauchy-Riemann equation. But it doesn't imply if a function is satisfies Cauchy-Riemann equation doesn't imply the function is analytic. So this is a necessary condition for analyticity. So the function is differentiable or analytic at a point, then f of z satisfies Cauchy-Riemann equation. Now, how to find uh, derivative of a function? That means what is the sufficient condition for a function to be analytic? So we will discuss what is the sufficient condition for a function to be analytic or differentiable, and how to find out derivative of a function by using Cauchy-Riemann equation. And so now our question is, what is a derivative of a function? So next is our sufficient condition. What do you mean by sufficient condition? If function satisfies this condition, then the result holds. The sufficient condition for analytic function. So what is sufficient condition? A function f of z is analytic if there are two conditions. First one, f of z is equal to u plus iv satisfies CR equation, and second one, partial derivatives ux, uy, vx, vy are continuous. That means a function f of z is analytic if first condition it must satisfy Cauchy-Riemann equation, and second condition all partial derivative ux, uy, vx, vy are continuous. Then derivative f dash of z is equal to, then derivative of a function f dash of z equal to ux plus ivx, or you can find f dash of z equal to or we can write vy minus I uy. So this is the way to find out the derivative of a function. So derivative of a function is simply ux plus I vx if f satisfies Cauchy-Riemann equation, and second condition if all its first order partial derivatives are continuous. Okay, so here we discuss what is analytic function and what is a necessary condition. CR equation is necessary condition, and we discuss the sufficient condition, and we discuss what is derivative of a function. Okay. Now we will do problems. We will do few problems. So this is the problem set, and I will send you this problem set 3, and we will discuss some problems here. Okay. So these are the questions, important questions for your examination. So the first question we will discuss. Verify Cauchy-Riemann equation for the function. So we know that e raised to z is a analytic function or differentiable function. We know that e raised to z is exponential function. This is differentiable. So now the question is verify Cauchy-Riemann equation for the function f of z equal to e raised to z. So we will do this problem. And how to verify? We want to check whether ux equal to, we want to check whether ux equal to ux equal to vy and uy equal to minus vx. So solution, we have f of z is equal to e raised to z. Now we can write e raised to z. Z is x plus iy. So this is equal to e raised to x plus iy is e raised to x into e raised to iy. This is equal to e raised to x into e raised to iy by Euler's formula. This is cos y plus I sin y. So this is equal to e raised to x cos y plus I times e raised to x sin y. Now here, what is u? That is real part. This is real part. E raised to x cos y. And what is imaginary part? Imaginary part. This is u. This is v. So v equal to e raised to x sin y. Now what is the question? Question is to verify Cauchy-Riemann equation. Now we will verify this. So for that, first we want to find out ux. What is ux? Partial derivative with respect to x. So e raised to x is e raised to x cos y. Now what is uy? Here we are differentiating u with respect to y. Then minus e raised to x. Derivative is cos y is minus sin y. So sin y. E raised to x minus sin y. Now what is vx? Derivative of x with respect to x. This is e raised to x sin y. And what is vy? E raised to x sin y derivative cos y. Now which implies. So now we want to check what is u of x. U of x equal to e raised to x cos y. What is v of y? E raised to x cos y. So u of x equal to v of y. So first condition satisfied. And second condition is what is uy? Uy is minus e raised to x sin y. What is vx? E raised to x sin y. So there is a minus in. So this is equal to minus vx. Thus f of z satisfies e raised to z satisfies CR equation. Okay. So this is the way to verify CR equation. Now, okay. Now we will do next problem. Verify Cauchy-Riemann equation for the function f of z equal to 1 by z, and is this function is analytic. So we know that 1 by z is a function which is not even defined at 0. So we have to check. So, so what is 1 by z? F of z. Here the question is f of z equal to 1 by z. This you can written as 1 by x plus iy. So this if we multiply with the conjugate, you will get x minus iy divided by x square plus y square. That is x plus iy into x minus iy is equal to x square plus y square. Now this can be written as x by x square plus y square plus I times minus y by x square plus y square. Now, now, what is u here? U equal to x by x square plus y square, and v equal to minus y by x square plus y square. Now we will find partial derivatives. So what is ux? Ux is equal to we will find the derivatives. Ux equal to x square plus y square into, we will use quotient rule, 1 minus x into derivative of x square plus y square. This with respect to x is 2x square divided by x square plus y square all square. So this is equal to x square plus y square minus 2x square. Sorry, 2x square. This is equal to y square minus x square divided by x square plus y square all square. Now we will find what is uy. If you differentiate uy, uy is equal to, if we differentiate this with respect to y, then what we will get x, okay, x square plus y square into derivative of x with respect to y is 0 minus x into derivative of this with respect to y divided by x square plus y square all square. So this is equal to minus 2xy divided by x square plus y square all square. So this is ux and this is uy. Now we will find out what is vx. Vx. If we differentiate this with respect to x, you will get minus of, I am taking minus outside, x square plus y square into derivative of y with respect to x is 0 minus, we are using quotient rule, minus y into derivative of x square with respect to x square plus y square with respect to x is 2x divided by x square plus y square all square. So this is equal to you will get y square. You will get this is 0. So 2xy divided by x square plus y square whole square. Now we will find out what is Vy. So now I will differentiate this with respect to y. So minus, I am taking outside, x square plus y square into 1 derivative with respect to y minus y into derivative of x square plus y square with respect to y, with respect to y. So 2 divided by x square plus y square whole square. So this is equal to minus of x square minus y square divided by x square plus y square whole square. Now we will check what is ux. Ux is y square minus x square divided by x square plus y square all square. And what is this? This is simply y square minus x square divided by x square plus y square all square. This is ux. So ux equal to vy. Similarly, what is uy? Uy equal to minus 2xy divided by x square plus y square. And what is vx? Vx is minus of, so we get ux equal to vy and vx uy equal to minus vx. And this satisfies everywhere except one point where it is not satisfied, it is not defined. എപ്പോഴാണ് ഇത് not defined ആകുക? When x square plus y square equal to 0, it is not defined. So there we cannot say it satisfies Cauchy-Riemann equation. Therefore f of z is analytic everywhere except z equal to 0. That means x square plus y square equal to 0 means x equal to 0, y equal to 0. That implies z equal to 0. And you know that at every point partial derivatives are continuous except when this denominator is 0. So denominator is 0 when x equal to 0, y equal to 0. That means z equal to 0. So f of z is analytic everywhere except except at these points. Now I will do next note this problem. I will do another problem that is very important problem and very easy. So this is might be asked in your GATE examination. Its problem is this. Prove that an analytic function with the real part is constant. So given how to do this problem, given that you have a function f of z which is analytic, and given that its real part of f of z, that is we know that u is constant, then we want to prove that f of z is constant. So what we will take, let f of z is equal to u plus iv, where u equal to k, a constant. And given f of z is analytic. So given that f of z is analytic, therefore what we can say, if f of z is analytic, there is a necessary condition f of z satisfies CR equation. CR equation. f of z satisfies CER equation. Now f of z satisfies CR equation. What is CR equation? Ux equal to Vy and Uy equal to minus Vx. So here, what is U? U is a constant k. Then what is Ux? If U is constant, then its derivative is 0. And what about Uy? Uy is equal to 0. So we get, already we have U is a constant. Now what, by Cauchy-Riemann equation, what is Vx? Vx is minus Uy, which is equal to 0. So Vx is also 0. And what about Vy? Vy equal to Vx equal to minus Uy, Vy equal to Ux. Okay, Vy equal to Ux is also 0. So we get Vx equal to 0 and Vy equal to 0, which implies if derivative with respect to x is and with respect to y is 0, then V must be a constant k2. So what we get? We get U is constant and and also V is constant. That is U equal to k and V equal to k2. This what is f of z? F of z is equal to U plus IV, which is equal to k plus ik2. This is a constant. Okay. So this f of z is constant. Therefore, we proved that any analytic function with a constant real part is constant. So we will do the